Honors Pre-Calculus Final Exam Review for 2013. We're looking at numbers 76, 77, and 78. So 76 we could almost write out and multiply, and it would be not too hard to do without using polar form. But so we're going to do number 77, and then 76 and 78 are done the same way. 78 has a little more difficult numbers to it. So on number 77 we have 1 plus I to the 20th power. So first, here's what we're not going to do. We're not going to write out 1 plus I 20 times and then FOIL them. That would be too much work. So what we're going to do instead is convert this 1 plus I, the 1 plus I, we're going to convert to polar form. Because in polar form, we can take advantage of an easy way to get powers, which has a very fancy French name, de Moivre's theorem. So we start by getting the polar form with our usual polar form equations. R equals square root a squared plus b squared, and theta equals inverse tangent of b over a. So our a is 1, and our b is 1. So it's important to notice that the b is the coefficient of I. It's 1. So b is not I, b is 1. So we have 1 squared plus 1 squared. So r is the square root of 2. And we can just work with r as square root of 2 like that. Now, for the theta, I have inverse tangent of b over a, so that's the inverse tangent of 1. I need to know what the inverse tangent of 1 is, so what I will do is think about my unit circle, and I will think, where is the tangent equal to 1? The tangent is equal to 1 here. Tangent is also equal to 1 down here, but the restricted domain of inverse tangent is from negative pi over 2 to pi over 2, so I'm going to choose this as the inverse tangent of 1, and that is at the angle pi over 4. So theta equals pi over 4. But I'm also going to remember that that pi over 4 for theta might not be exactly right. I have to check what quadrant I'm in to see if I have to add 360 or 180. So I'll look at where this 1 plus I is graphically. So 1 plus I, and there's my complex number there, and this is the angle. And the theta I have is pi over 4, and pi over 4 is right there. That is measured from the positive x-axis, so that means that this theta that I got of pi over 4 is in fact the right theta. If I were looking for a point down here in the third quadrant, I would have to add pi to get that 180 degree angle. But my angle here is right, so I can just use theta equals pi over 4. Now I can write my problem into polar form. So my polar form is square root 2 cosine pi over 4 plus I sine pi over 4. Now I have to do this to the 20th power. So we're going to raise this to the 20th power. Now that's easier to do in polar form because all we have to do is do the r, this is our r, we're going to do r to the 20th power. And our theta is going to go, that's not a theta, that's a phi. Our theta is going to go times 20. So the theta multiplies, the r goes to the power. That is what de Moivre's theorem says. So now I have to be able to do the square root of 2 to the 20th power. Now you can go to your calculator to do that because it will give you an exact value. But just to sort of think it out, use our brains a little bit. What does it mean, square root of 2 to the 20th power? Well, square root of 2 is 2 to the 1/2 power, and we have to the 20th power. And when I have a power to a power, I multiply those two exponents, so that's 2 to the 10th. So square root 2 to the 20th power is equal to 2 to the 10th power, and as every good computer programmer knows, that's 1024. This number of bytes in a kilobyte, in fact. So square root 2 to the 20th power is 1024. But you could do that on your calculator. We are not even asked for exact values, so we could do it all on our calculator and not lose any points. But on the exam, it might ask you for exact values. Either way, your calculator will give you an exact value for square root of 2 to the 20th power. All right, so now we're going to take our theta and we have to multiply it times 20. So we're going to go cosine, let's see, pi over 4 times 20, if I sort of work out what that is as a scratch work, pi over 4 times 20 over 1, well, this would reduce, and 5 and 1, so it's 5 pi. So our theta is going to be 5 pi. And then we have plus I sine of 5 pi. All right, so we've multiplied our theta times 20. Now, we have to be concerned with this theta because it's too large. You remember what we said about the theta in degree form? We said theta has to be between 0 and 360, and if it's not, then we have to subtract off 360 to get a coterminal angle. So when we're in radians, we have to say that theta has to be between 0 and 2 pi. Well, 5 pi is clearly larger than 2 pi, so again, we're going to have to subtract off some coterminal angles, and this time, instead of subtracting 360, since we're in radians, we'll subtract 2 pi. And hopefully you can see that if I subtract 2 pi, I'm going to get 3 pi, which is still outside of the domain for theta. So I'm going to subtract 2 pi again, and now I just get pi, and pi is indeed between 0 and 2 pi. So this is the real theta that I want to use, and so as a final step, I will rewrite this number in polar form. I'll write it with the correct value for theta. So it's 1024 cosine pi plus I sine pi. Now, the problem asks me to write the answer in rectangular form. So that means that I have to evaluate that cosine of pi. Cosine of pi is -1, and sine of pi is 0. So this gives me -1024 plus 0, or just -1024. So this is a nice rectangular form where we have a is -1024 and b is 0. b equals 0, but it's still a complex number in rectangular form. So there's how we're going to do a complex number to a large power.